Chapter 18, Part 4. Okay. More reactivity, and kind of a weird reaction. We'll start. We've been talking a little bit about halogenation of ketones, and if you take acid and you add chlorine, you will set up under acidic conditions the enolization of a ketone, assuming it has an acidic, removable, epimerizable, deprotonatable proton next to the carbonyl, with, that can be line up with the p orbitals of the ketone, and then chlorinate that, and it goes directly to the ketone and generates hydrochloric acid as the byproduct, and that's generalizable to really all of the halogens. And you can do that once if you'd like with chlorine or with under acidic conditions. But if you do that under basic conditions, and the classic is using iodine. We'll get to the Helvol-Hardzelinsky momentarily. You will set up an equilibrium again, and I'm going to draw this as the enolate, because we're using basic conditions. Even that will be protonated in the water, because you always have water around sodium hydroxide, and then that will attack the iodide, and you get the alpha iodo ketone, which is super reactive as a electrophile. But if you're making it under basic conditions, the iodide, which is still electron withdrawing, it is more acidic, and so that will react faster, and now you'll have the diiodo acetone, the 1,1-diiodo acetone, and now it has two electron withdrawing iodides, and I'll use bad English and say more faster, and you now have three iodides, if you can believe that, and these are big, but they all end up on the same carbon. And back in the day, you will get, you would use this if you wanted to demonstrate that you had a methyl ketone, or see if you had a methyl ketone. This is a test for this is the haloform reaction. It's the iodoform reaction. If you're using iodide, you form 3-iodo 1,1,1-triiodo acetone. Now there's no more acidic protons on this side, but rather than enolize on the other side, finally, you'll remember that there's a resonance structure to ketones. And that resonance structure looks like this, where you're just taking the electrons in the p orbitals and moving them up onto the more electronegative oxygen. So now you have this positive charge down here, right next to this carbon with all of the halogens on it. That is a destabilized ketone. And so what happens is your sodium hydroxide base here acts as a nucleophile. Now it's doing this actually all along. So this is adding to ketones. Well, sorry, it's not the enol. It's adding to the ketones reversibly all the time, but it's reversible. You don't actually see it. It's a background reaction. But here, it adds and while that is reversible, of course, right? I mean, this could do this. Electrons come back down and kick out the hydroxide. But it turns out that the triiodocarbon with these electron withdrawing groups is now a leaving group as well. And so occasionally, it doesn't matter whether this has to add and be kicked out a bazillion times, a bazillion and one time, that it's not that it takes the path of breaking the carbon-carbon bond. You get acetic acid and iodoform anion, which of course we are under basic conditions, so this is going to be deprotonated by something, but for the sake of drawing this out, that will protonate the iodoform, and you get triiodomethane, which happens to be a solid. Not just a solid, it's a yellow solid. And that precipitates out of the reaction. And that is, so if you take an unknown compound and you treat it with base, sodium hydroxide, and I2, and you see a yellow precipitate form, that is a positive iodoform reaction. And in the old days, before NMR and mass spec and things like that, this was a chemical test for methyl ketones. Okay, only methyl ketones. Because only methyl ketones can get 3 halogens on there and become a leaving group. So if it was an ethyl ketone, you might get the diiodo. That does not act as a leaving group. So this is a test only for methyl ketones. It's also a way of taking a methyl ketone and turning it into a carboxylic acid. Okay, so there's different ways you can look at these reactions. So that works with chlorine and bromine and things like that. So chlorination. Where is chlorination a big part of your life? And maybe it's not a big part of your life, but let's say you're setting up a goldfish aquarium, or maybe not a goldfish, something a little more expensive and a little more exotic. You know, say you want to have an aquarium full of beautiful little fish from the aquarium store. I used to have that with my sisters when I was growing up. And what you typically do is you fill your aquarium with water out of the tap. Why not? It's good to drink. Ought to be good enough for the fish. But you let it sit for a day. You let it sit for a day because you want to make sure that the chlorine in that water has evaporated, and it will. But it does take a little bit of time, and so it's better. And so if you're going to have an air pump in there, so you can get that going, and that'll help get the chlorine out. And once in a while, there's enough chlorine in there in drinking water that you can, out of the tap, that you can taste it. The chlorine is not going to hurt you because there's not enough of it there. In the realm of naturally occurring organics that makes it into your drinking water, and that could be acetone, it could be any other methyl ketone, you're gonna generate the Cl3 chloroform. That's what people used to use to knock people out in the movies, a handkerchief full of chloroform, because that is it will knock you out. Reversibly, of course, if you don't get too much of it. This is carcinogenic. So what I'm telling you is if your city chlorinates its water, you will have very, very small quantities of chloroform in that water. Is that something to worry about? Actually, no. Because, yeah, I don't recommend smelling and drinking and playing with chloroform every day. We do it in the lab all the time. You'll recall that NMRs are usually run in deuterochloroform, and that's easy to make because this is acidic, and so if you take a little NaOD and D2O, you can do the proton deuterium exchange, and that's because this is slightly acidic. We do this all the time. We don't worry about the fact that it's a very, very minor carcinogen. It's very low in its carcinogenicity. But I'm just telling you, it's going to be there. That's a good thing. It's a good thing because if you're not sterilizing the water, you're going to end up with dysentery and typhoid and things like that. And so you're much better off chlorinating the water. There are other ways, ozone, for example, to sterilize drinking water, but they're more expensive. So, taxes versus safety, it's a cost-benefit analysis. But now you know where this comes from. It's this haloform reaction that occurs. So, the Hell-Volhard-Zelinsky is related to this. I jokingly refer to it as the Hell-Volhard-Zelinsky reaction. It's a reaction that was discovered by these three guys more or less simultaneously, and so we try to honor that by using all three. Kind of like the Horner-Wadsworth-Emmons reaction. I'm sure you can hear those 3 dogs next door. They just had 14 puppies over there, and I think they're all spoken for. That was a planned birth. I am a member of Planned Parenthood, longtime member. Okay, so let me go back to basics here. If you take a ketone or an aldehyde and you add acid, you will promote catalytically promote enolization. Draw it that way this time. That's in equilibrium. The acid doesn't change the ratio, it just changes how fast this equilibrium is established. However, and that has to do, of course, with the fact that you're protonating the carbonyl and then the proton falls off. Well, if you take an ester or an acid, and so you could imagine this could be self-promoted, one could imagine you protonate carbonyl and lose the proton, a different proton. Oops. Proton that I was just starting to draw in. And you get this dihydroxyalkene. Well, you know, while in principle there's nothing wrong with that, but in practice that doesn't happen. Not formed. It doesn't happen because there's a resonance structure here. Which stabilizes the acid or the ester they're more stable, and therefore no enolization. Period. Exclamation mark. You don't get enolization. So if you want bromoacetic acid, what do? You can't brominate it under acidic conditions. And if you treat it with base, you're just going to deprotonate the acid, and then you can make the dianionic dihydroxyalkene, this with 2 negative charges. You need a really strong base for that. And I'll tell you what that strong base is soon. LDA are the key letters there. So this is a problem. This is potentially a problem, and it's a problem because an alpha bromo esters are actually really good substrates for SN2 reactions, and there's lots of different things you can do with those, but you have to be able to make them. And I guess I've run out of time, and I'll do that in the next lecture.